Hello everyone, today we are going to verify a classical structural problem from the Shigley's Mechanical Engineering Design textbook, the deflection of a cantilever beam with a concentrated end load. As shown in this slide, we are analyzing a 400 mm steel beam fixed at one end. Here are our simulation parameters. F, concentrated force 1000 newtons applied at the free end. Length L 400 millimeters. Diameter D 20 millimeters. Material properties: a structural steel with a Young's modulus of 200 gigapascal and a Poisson's ratio of 0.3. According to the Euler-Bernoulli beam theory, the maximum deflection at point A, the end point, is calculated using this formula. Our goal is to see how accurately Abaqus FEA matches this analytical solution. Okay, now let's move into Abaqus and follow the modeling process step by step. Geometry creation. In the part modulus, we should create a 2D planar wire, 2D deformable wire, approximated size 2 times of the longest dimension. So it's 800. A wire or a line from 0 point to 400 0. We check it. Okay. The part is created. In the property module, we should define our steel material. In the mechanical elasticity elastic property, Young's modulus is E2E5 in megapascal and 0.3 Poisson's ratio. It's very important to consider unit consistency. For example, in this case, millimeters and newtons. So we have megapascal for Young's modulus. If we enter meter, we should consider Young's modulus in Pascal unit. Okay. For next step, section assignment, we create a circular profile with a radius of 10 millimeter. Then we define a beam section and assign it to the entire wire. So we create a section with the category of beam and type of beam, and the profile is circular, and dimension is 10 millimeter, R for the radius, and the material is material 1 that we created in the previous step. Now we should assign this section to our wire. Assigned it. And the most important step, this is a vital step. Using the assign beam orientation tool, we define the local axis of the cross section to ensure the moment of inertia is correctly calculated about the bending axis. Okay, so we use the beam section orientation. I consider the default orientation that you see here. The tangent axis is the axis of the beam. In the assembly module, we import our beam part independently, and in the step module, static general step with default setting we have no interaction in the load module. We apply an encaster or fixed boundary condition to the first vertex. Then we apply concentrated force of 100 newtons in the y direction at the free end. Okay, so we from the step initial boundary condition of fix, symmetry or encaster is chosen. Encaster, this end is fixed, and the other end in the step 1 concentrated force, this vertex, CF2 in the y direction, of course, has opposite sign because of opposite direction, 1000 newtons. We have load 1 at the other end of this beam. So we have boundary conditions and loading in our analysis. Okay, now in the mesh module, we select our seed, apply it. It's okay, but I want just one element now, and then mesh convergence will be checked. Don't worry about that. Define our element type B21. It's okay. We have just one element in our beam. We can now analyze our problem. So in the job module, I create in model 1, job 1. Default setting is accepted, and submit our job. Okay, problem solved. The result is here shown, and U in the y direction is shown here in this table, approximately 13 millimeter in the opposite y direction. Okay, and now I'll note down the y value to check the convergence, 12.68 as y1. So in the mesh module, first we copy model 1 and create model 2. In the model 2, the dimension and the size is divided to 10 or 10 times our elements. So we have now 10 elements. We can that 10 elements have been generated on instance. Now in the job module, create job 2 in model 2, submit this job and wait for job completion. Okay, the job is completed, and the result is here in 2 direction. You see the smoothness of result is better than this result. It's a straight line, and now we have a smooth line here, and the y2 y in analysis 2 is 13.5 59. I do the same work now in model 3. Forty is divided to 10, and new mesh generated, and we see 100 elements have been generated on instance, and job tree on model tree is created now and submitted, and wait for job completion. Now the third job is completed, and the result shown the magnitude of U2 Y3 equal 30.60. Now we see that the Y is converged, and now we can say mesh convergence is checked. We see Y with just one element, Y2 with 10 elements, and Y3 with 100 elements have these values for the deflection of the beam, and results are meshless now. Okay, for conclusion, we understand that the finite element analysis maximum beam deflection is 13.6, and we should compare this solution of finite element with the analytical solution. For analytical solution, we can use the calculator of Abaqus, but I prefer to use MATLAB for calculation. It's not different, just substitute the values and new. Okay, now I, the moment inertia of area, okay, the deflection of the beam now is calculated F times L power 3 3 times E times I, and the result is 13.58. So the difference between theoretical Y and finite element Y is approximately 0.2%, and is a nearly perfect match. This confirms the accuracy of our FEA setup. Thank you for watching. If you found this helpful, please hit the like button and subscribe to SimAI for more engineering deep dives.